Okay, let's take a loop at that magnetism and induction take-home test. Let's look at the multiple choice first. So the first question says, we've got a particle um, that's got a charge plus E, so that means it's like a proton and mass m, so one elementary charge, right? Moves with the speed v, perpendicular to the uniform magnetic field B, directed into the page. See all the x's, that's B field going into the page. It makes a circle of radius r, so it's going around. It's either going around like this or it's going around like this. They'd like to know which way it would move and an equation relating the velocity and the radius of that loop that it travels in. So what I would do is I would say, well, first of all, I'm going to go ahead and do my right-hand rule. We're doing force on a charge moving across magnetic field lines is QV cross B. So I might take a guess first. Let's imagine, I'm going to look at the bottom edge of that circle. Let's guess it's going to the right. If it was going to the right, I take my right hand and I do my fingers with the first vector, V cross B, so velocity. Say, which way should my hand face? So that when the fingers bend, they'll point along the magnetic field lines, which is into the page. So like this force would be up. Hey, that's toward the center of the circle. That's the way we want. So in fact, it is moving counterclockwise. And so then we ask, we want to have an equation for relating the radius of the circle and the velocity. So I'm doing a circular motion calculation, and that's going to look like, some of the forces in the radial direction is mass times acceleration centripetal, which would be mv squared over r. That force is the magnetic force, which is qv cross b. One of the v's is going to drop out. So let's see here. I'm looking for, the charge q. The charge is plus e, an elementary charge. So that gives me eb is mv over r. If I move the r over, I would have EBR is mv. EBR is mv, that's choice C. So problem 1, we're going to go with C. All right, problem 2, the period of revolution of the particle, the time to go around once. Well, it's going in a circle. We know that speed is the distance divided by the time, right, to go around once. Distance around once, 2 pi r divided by time t. Rearranging, then, that period would be 2 pi r over v. And v, if I rearrange this, my v would be what? Multiplied by r over m. EBR over m. That goes in there for v. So I'll have 2 pi r over, so I'm going to divide by EBR of m, so I multiply by the reciprocal. M over EBR. The r would drop. I get 2 pi m over EB, right? 2 pi m over EB. Okay, that's choice C. All right. Problem 3. A wire of radius big R has a current I uniformly distributed across the cross-sectional area. Ampere's law is used with the concentric circular path of radius R with R less than big R to calculate the magnitude of the magnetic field. Sure. Inside the wire at distance R, right? R less than big R. Okay, so I've got this wire. So I've got this big thick wire with a radius big R, and I'm trying to find the magnetic field, and I've got this current flowing through it, and the current is flowing a nice evenly distributed throughout the wire, uniformly distributed, right? And they want to know the magnetic field strength at some distance little r out from the center. So if I was going to use Ampere's law, then I would do a little path, right? I'm going to make that path, let's see here, I'm going to make that path go around like this with a radius r. That's meant to be like, you know what I mean, right? You know what I mean? It's like a circle of radius r. Oh, that's really sloppy. The B field lines are going to loop around the current, right, like this. So my B field would be going around like that at point r. You know what I mean? At distance r. So my little area, my little path length, when I do Ampere's law, I pick an Amperian path is what I was doing there. And I'm saying, hey, my integral over that path integral over that closed path of B dot dl is mu naught times the current inside. that path around is a circular path, so it's at a constant r, and the B field will be a constant strength along that path. So that path length would be 2 pi little r. Like the B is a constant by symmetry, and the integral of all the dLs will just be the path all the way around 2 pi r. Mu naught is mu naught. The current inside, well, the thing is, in that then I'm only getting the amount of current that's going in, this part out of that whole current. So I'm just going to say it'll be, because it's evenly distributed across the wire, it'll just be what fraction of the cross-sectional area is going through this path. So the fraction of the current times the total current. So it'll be the area in the path over the area of the whole wire, that fraction of that total current in the wire, right, is the current that's in. So if I do that, let's see, the 2 pi's will drop out. So that's what I'm getting. Does that look like any of these options? B times 2 pi little r mu naught little r squared over big R squared I. Yeah, these first three are all correct left side. I want choice B. So for 3, I want choice B. All right, moving on to problem 4. Problem 4, 2 parallel wires, each carrying a current I, repel each other with force F. If I double both currents, what happens to the force? So if I got like parallel wires, right, then, each one of them will make a magnetic field, right, that'll loop around it, right? And that magnetic field, as it loops around, then the other current will be going through that magnetic field, and so that wire will get pushed. The force on a wire is IL cross B. And the magnetic field strength made by a wire is mu naught I over 2 pi r. I have that memorized. Magnetic field from a long straight wire. And so taking a look at this, then you'd say, well, gosh, this is what's going to go in there for B. If I double this current and I double this current, 2 and 2, that'd be like 2 times 2. It'll be 4 times the force. And 4 times the force, that is choice C. All right, that's that first page. Going to the next page. Problem 5. A circular current carrying loop lies that the plane of the loop is perpendicular to a constant magnetic field of strength B. Whew. Okay, so if I've got a loop and the plane of the loop is perpendicular to the magnetic field, so the magnetic field is going like straight into that cross-sectional area, you know what I mean? Suppose the radius r of the loop could be made to increase with time, so that, yeah, so like I've got, so maybe I have like a loop of wire, right? And I can make the radius increase, right? Make it get bigger, 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 so I'll get more and more flux through in that loop, right? So suppose the radius of the loop could be made to increase time so that the radius is a times t, where a is a constant. What would be the magnitude of the EMF to be generated around the loop as a function of t? So I'm going to say they want the magnitude of the induced EMF. Induced EMF, that's Faraday's law, negative d phi b dt, which is the rate of change of flux, and the flux is going to be my integral b dot dA, right? And you say, hey, the B field's a constant, so that all over that area, but so the area, it's just going to be that constant B field times the area, right? Because it's they said it's going to be the B field's plane of loop perpendicular to the B field, so the B field's going straight in, so it's going to be like a cosine of 0. The plane of the loop, right? The plane of the loop is perpendicular to the B field, right? Well, the area vector of a loop sticks straight out of it when I do this calculation. The area vector goes straight out of the coil face of a loop. So the B field is nice and parallel to the area vector. So it's a cosine of 0, or maybe a cosine of 180, you know. But you see what I'm saying? So this A, that's the area vector, it sticks straight out. Just like the area vector, whenever you calculate a flux, right? The area goes straight out of the plane. So anyway, there we go. Normal to the plane. So anyway, so when I do this, it's just going to be BA is the point. And what's the area? Well, the area it's a circle, so it's going to be pi r squared, right? Okay, now I want the d dt of this to get the EMF. Well, the b is constant, pi is constant, derivative of r is changing as what? R is a times t. Kick the b, kick the pi out. I want the derivative of r squared, and r squared is at, right? So you say, okay, that's going to be a squared, and then derivative of t squared, that's going to be a 2t. So that's my EMF. What are my choices? Does one of those look like it? A 2, a pi, a b, an a squared, and a t. Well, yeah, that's I guess a is the choice, huh? All right. So 5 I'll say is a. Okay. Moving on, number 6. A charged particle can move with constant velocity through a region containing both an E field and a B field only if, and this is something we know from like talking about the mass spec, or talking about the Hall effect, or talking about motional EMF, that charges are going to flow in the conductor until the fields balance, right? The forces from the fields balance. To get that to happen, I need the E field and the B field to be perpendicular to each other. For example, in motional EMF, you're pushing, maybe like a bar of metal moving across a magnetic field. Say the B field's making X's going into the page. Then as like the electrons, for example, electrons in it are moving to the right then. You say, what would happen to them? Well, as they move to the right, V cross B forces, but because they're negatives, the force is this way. Well, the electrons would start to then get shoved down here, right? But then I get all these negative charges built up down here. Dunk, 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 dunk. The electrons just leaving positive charge behind here. Are the electrons just going to go forever? You say no, because eventually this moving sets up, I set up an electric field in there, right? Gets set up by this charge, induced separation of charge. And so I'm going to have an E field like that. And so the E field lines go this way, force on an electron is that way. Once enough charge builds up, the force from the E field will balance out the force in the B field, and then they won't move anymore. So anyway, the point is, my B field and my E field got to be perpendicular to each other, because the B pushes perpendicular to itself. The B field lines push sideways to themselves. So they got to push, that's what it takes to balance them out. So we are saying we want the E field to be perpendicular to the B field, and that is choice B for number 6. Like I said, this is just one example of that. We get that same thing happening with the Hall effect. When I've got current flowing down a wire across magnetic field lines, inside the wire I set up just like this, electrons get pushed. Say there's a wire going this way with current. Let's just stop. Like I said, in the mass spectrometer, you do the same thing, same trick, crossing E and B fields to make the forces balance. 7. I've got a conducting loop of wire that is initially around a magnet, and we're going to pull that loop away, right? The loop that is initially around a magnet is pulled away from the magnet to the right, which induces a current in the loop. What's the direction of the force on the magnet and the direction of the magnetic field at the center of the loop due to the induced current? Okay, so I've got my magnetic field lines shooting out the north pole of the magnetic field lines going to the right. As I move the loop further away, the field gets weaker, less field lines go through the loop. So I'm having a decrease in flux to the right. And so you say, well, gosh, that changing flux would make a current flow around in the loop. And you say it's got to move, make the induced current in the loop has got to flow to make field that fights against the changing flux. I'm getting less and less flux to the right, so current has to flow to make more flux go to the right. I'm going to use the third right-hand rule. That's the one where that's just for loops of wire. I make my fingers curl with the current and thumb points the direction of the field in the middle of the loop. I'm trying to make more flux go right to fight against the change, right? As I move it, less goes through, so I got to make more go through. So I need it to go like this. I need to go up and back, down and front the current, and make more flux go to the right. Well, if I do that, right, I'm trying to make induced flux to the right, so that's going to be choice either A or C. and you say, now the thing is, when I do that, I'll be making current flow around. You say, well, it takes energy to make this flow around. Where's the energy come from? The electric forces have to make you do work to push the charges around. So as I pull this away, you say, I'm trying to go away from the magnet, so the magnet's got to get pulled back towards it. So the magnet's going to get pulled to the right. Induced field to the right. A is the choice we want. In other words, I'm trying to pull this guy to the right. When I induce like this, that means it's going to make a south pole on the left side. That induced field is going to be going out the right, be going in the south. It'll make a south that tries to pull the magnet along, fight against what we're trying to do, pull them apart. So yeah, so A is the best choice for number 7. All right, one more on that page. Problem 8. I've got a square loop of wire containing a current I that is initially in the plane of the page, right? The loop of wires in the plane of the page, locating a uniform magnetic field B that points toward the bottom of the page like this. Which of the following shows the correct initial rotation of the loop due to the force exerted on it by the magnetic field? Okay, now charges don't get pushed when they go along the B field line, so there's no force on this side or this side of the loop. However, there will be forces on the bottom or top edges. Take a look at the top. Current goes to the left, magnetic field going down, doing my QV cross B or IL cross B. Fingers with the current, the way positive charges are moving. Which way do I need my hand to face as they go across that top moving to the left? Well, I need my hand to face so that when the fingers bend, they'll bend the way the magnetic field is. The magnetic field, IL crossed into B. Forces out of the page on that top part. On the bottom, they're going to the right. IL cross B down into the page. So this thing's going to get spun like this. It's going to flip around a horizontal axis. Well, the only one that spins around a horizontal axis is C. That is the best choice. Can't really tell like which way the arrowheads go pointing on this little loopy indicator because of the crappy font. Sorry, but definitely this is the only one that goes around a horizontal axis. That's the one we want. Okay, and it should be flipping like this. Yes. All right, that's that page. All right, last page, page 9. I gave you a bonus one. I gave you 13 instead of 12. Okay, here we go. 9. One of Maxwell's equations can be written as E dot ds. Hey, that's Faraday's law of electromagnetic induction is what that is. This equation expresses the fact that a changing magnetic field produces an electric field. Yeah, I got changing magnetic flux. That should be phi sub b. That should be specific there. Sorry, that's magnetic flux we're changing, making the E field. They were trying to be tricky and not put a label on that and see if you knew that. Changing E field makes a B field. No, we're not changing the E field in this equation. That's magnetic flux. Net magnetic flux through a closed surface depends on the current inside. That's Ampere's law, which this is not. That would be integral of B dot ds and proportional. Anyway, we'll stop there. Net electric flux through a closed surface depends on the charge inside. That's Gauss's law for E fields. And changing E, oh, by the way, going back up here, B, changing electric field makes a magnetic field. That's the Ampere-Maxwell law. Electric charge is conserved. That's not what this is saying. A, changing B field making an E field. That's A. Alrighty, moving on. I've got 3 parallel wires, X, Y, and Z. I can see the currents going down, down, and up. They each have a magnitude I and are in the currents shown above. Wire Y is closer to X than it is to Z. Okay, that's like it looks in the picture. The magnetic force on Y is 0 into the page. Okay, so direction of the force. Okay, so wire X, if the current's going down, I'm going to use the second right-hand rule. Grab the wire, thumb in the direction of the current. The way the fingers loop around is the way the field goes that it makes. So wire X, that current, is going to make field coming out of the page where wire Y is. Okay, what about this one? Z here, current's going this way. Grab the wire. It also makes field out of the page. Both these guys, X and Z, are making field shoot out of the page. So current Y is going down through a field that's going out of the page. So if I do the right-hand rule, this is going to be awkward in the camera, but I'm going to do my IL cross B. My I is this way. Which way do I want my hand to face? So that when the fingers bend, they'll put it on the B field out of the page. IL cross into B, force is going to be to the left. All right. So that is choice E. Alrighty, takes me to 11 and 12 here, dealing with this little circuit. This switch that's been open for a long time, so we can assume the current in the circuit is 0, right? I then suddenly I'm going to close the switch. I'm going to turn the circuit on, right? I've got this 12 volt battery, a 6 ohm resistor, and a 4 Henry inductor. What's the current in the circuit when the switch has been closed for a long time? Okay, when it's been closed for a long time, the inductor will have reached its full magnetic field strength inside the inductor, so it's not going to fight the current anymore. It's going to have no induced voltage at all. And so basically it acts like a bare wire. And so after it's been closed for a long time, basically it's just the current running around. This is doing nothing. So it's just going through 12 volts over 6 ohms then. There's no delta V over the inductor once it's at full strength. And so you're like, oh, 12 volts over, I'll just use a delta V as IR. Sorry, we're on to question 11 here. Delta V is IR, right? Trying to find the current. I is delta V over R. The delta V is 12 volts and the R is 6. That's going to be 2 amps. 2 amps is choice C. All right, and then question 12. What's the potential difference across the resistor immediately after the switch is closed? Potential difference, that's the delta V across the resistor at first, in the first instant. In the first instant, that inductor is going to fight to make it so that you cannot jump currents. It's going to make the current have to build from 0. And so at the first instant, the current will start from 0. When there's no current through a resistor, there's no delta V across the resistor, right? Because delta V is IR for a resistor. And so the potential difference across the resistor in the first second is 0. So it's going to build from 0. Which takes me to question 13, last question. Yeah, got to have a goodie for the last one. Here I've got a sheet of copper in the plane of the page connected to a battery over here. That's going to push electrons around in the wire, right? Electrons will drift then through the copper toward the bottom of the page. Yeah, they're going to go this way, right? This is the high V side, so the current would flow this way. Well, the direction of the electron flow is opposite. So electrons will be moving through the copper plate this way towards the bottom, right? The copper sheet is in a magnetic field B directed into the page, right? That's all those X's, right? It's in a magnetic field. These 2 points, P1 and P2, are points at the edges of the strip. Which of the following statements is true? You say, okay, this is all about the Hall effect, okay? As the electrons move through that metal, right? Here we go. Here is that chunk of copper, and my electrons are moving down. So they've got a velocity that way, but they're crossing a magnetic field that goes into the page, and so those electrons would get pushed, right? Which way the electrons get pushed? Well, I'll use my right hand rule, QV cross B, charged particle moving across magnetic field lines. Which way do I need my hand to face? Oh, this is awkward. V, fingers curl down to go along the B field, so the electrons, they get pushed to the right. You say, but wait, they're negative charges, so they actually get pushed to the left. So electrons are getting shoved to the left by the magnetic field. FB is to the left. So that means this left side would start to charge up negative, and the right side would start to charge up positive. That voltage that gets set up between the edges of the conductor, this is called the Hall effect. Okay? It's Hall effect, or this is called a Hall voltage. And that's the way like a lot of magnetic field detectors work and magnetic field sensors work, is by measuring that Hall voltage. So you can figure out how strong the outside field was to make that happen. Anyway, the point is, if electrons get pushed here, this is the low V side, this is the high V side. So that right side, the P2 side, is the high V side. So we want P2 is a higher potential than P1. That would be choice B. That would be my answer for 13. And that's the multiple choice. Looking at that, it looks like my answers to the multiple choice questions are as follows. There we go. You can see all my let me see all my answers now. All right. So I got CCBC, AAAC, AECAB. And let me encourage you when you're working multiple choice questions to feel free to take little scribbles and notes on the blank part of your bubble sheet. You should be drawing little diagrams and working stuff out to figure stuff out. It is, and you can draw right on the diagram on your test, right? So you don't have to worry about that. But the point is that you should be taking notes and figuring things out. Don't be trying to do it all in your head. Okay, that's a sure way to make a silly mistake. So anyway, all right, that's it.